Hi, I'm Dr. Stuart Grey, a senior lecturer in the James Watt School of Engineering, and today I'd like to talk to you about engineering design. I'd like to talk to you about some of the processes we develop for that and some of the key skills you'll need as an engineering designer. So engineering design is a process we use to try and tackle some of the world's biggest problems. And that process can be quite simple. It could be 3 simple steps, for instance. It could be determining the need, the problem we're trying to solve. It could be then coming up with a vision to try and meet that need and then delivering on that vision. So the need might be, we need to get from A to B really quickly. That's the need. The vision might be, let's take all the technology from the Concorde, update it for the 21st century, and then we've got a supersonic business jet. And the delivery part is just build the jet. From that, it might seem that that delivery part is actually the hard engineering thing we're doing. But it's a mistake to ignore the needs and the vision because they're the most important part from a human aspect and the bit that can't be replaced by technology. One of the problems with a simple 3-step process like that is that it's linear. We just go through it once, and the chance of us coming up with a good solution first time is very, very low. So instead, we want to sort of maximize our chances and do what's a cyclical or iterative process. So an example of that might be, first of all, define a problem, then collect information on that problem, ask questions, do some research. Then we brainstorm and analyze potential solutions, as many as possible. Then we develop a small number of those solutions to a state where they can be tested. Then we test them or gather feedback. Do they work? Yes or no? Why not? What happens? Things like that. And then we take in everything we've learned in that testing, gathering feedback stage and apply it to our designs, improve our designs. But to make this a full circle, to make it something we can go through again and again and again, we have to take all the knowledge we've learned right the way through that process and use it to redefine our problem. So this is a really important point. The process isn't necessarily to come up with new designs or new solutions. It's to get a better and better understanding of the problem itself, because the better understanding of the problem we have, the more chance we have of actually solving it. Or ideally, not doing anything with it at all and negating it in some other way. An example of some people using this process would be the Wright Brothers. Obviously, they're famous for developing the first sustained powered heavy-than-air flight. They weren't aerodynamic experts who came up with new theories. They'd read the literature, right? They were at the cutting edge of the time. They'd read the papers produced by the universities, but they were bicycle sales and repairmen. What they did was rigorously follow a design process where they defined their problem, they tested ideas, and they did that again and again and again. And they put a large amount of effort, a disproportionate amount of effort, into the testing phase. They built tools just for testing their designs. They built wind tunnels for testing models. They built sample wings at full-scale mock-ups. They spent a lot of their time testing and going round and round and round. And they had this fundamental knowledge from the theory, from the aerodynamic theory at the time. But what they did was build on that with their own experience. As they spent years working through this design process, they got more and more experience until they could marry the two together. And really, then they were the world experts. And they're the world experts for a number of years after that first flight. It took people a long time to catch up. So the key thing there, that testing phase allows us to correct our errors, right? So fundamental parts of a design process are an iterative process. So we can do it again and again and again and hopefully improve each time. We have an error correction step there. So we're looking to actively correct our errors. Otherwise, we're doing the same thing again and again, making the same mistakes again and again. And lastly, we need some knowledge, either from theory or from experience. So stuff we've experienced and we've learned on the way or in our lives in general. So we have these different parts, but which is key? Which comes first? Which is the most important? Is it the iterative error correcting process or the need for knowledge? Now, luckily, we actually have an example of a process that produces incredibly complex solutions just with an iterative error correcting process and no knowledge at all. And knowledge in these terms are useful explanations about the world. There are lots of different definitions of knowledge, but that's what we use as engineers. So is it something useful we can use? And in terms of useful knowledge, evolution. It has no useful knowledge created. A dog does not know why its nose works the way it does. An eagle does not understand why its eye works the way it does. It doesn't have to. It just uses it. What it has is an excellent error correcting process. The environment is correcting any errors in terms of can this animal live in that environment. So that iterative process is working all the time and it gets to incredibly complex solutions. Now, the problem is it takes millions of years. And we don't have time to tackle the problems facing us as humanity at the moment. We don't have millions of years, right? There's going to be massive issues worldwide in the next 100 years. We've got to tackle them quickly. So the way to think about it is we need that iterative structure. We need that error correction. But we also need that knowledge, and that knowledge is a fuel to the fire, right? If we want to do things quickly, we need to add more and more knowledge. Now, this knowledge can take a few forms. Again, the theoretical knowledge or the experiential knowledge, let's say. But it's all built on one foundation, and that foundation is mathematics. Because people think of engineering, they think of mathematics, and with good reason. But this isn't mathematics in terms of remembering equations or doing a 3-page derivation in an exam hall. This is mathematics in terms of understanding the fundamental principles of how the universe works. Abstract relationships, how one thing can be taken from one domain and applied to another. And if we don't have that foundation, we can't really use the knowledge. That's why we need a strong mathematical background as engineers, because we've taken ideas from one place and applying them somewhere totally different. And we need to be confident in the maths to do that. So that's a fundamental aspect of what we do is the mathematics, but it's foundational. There's one real skill that we need as engineering designers, and that is because knowledge is created by us as people. So when we're solving engineering problems, we have to do it together as a team. There's no single player mode for engineering design. And we want lots of people on our team, but we don't want the same sort of person. Otherwise, we've got the same sorts of knowledge. So what we're after is as diverse a team as possible, diverse in terms of experiences, diverse in terms of domain, diverse in terms of solution they've seen. And if we can get that diverse team, we really stand a chance of tackling these big problems. This leads to the key tool for engineering design, and it's to work in that team. It's language and communication. We have to understand each other's point of view. We have to be able to understand clients or customers or the world's needs. We have to be able to communicate very technical content to each other and different solutions to each other. All that has to happen very rapidly in a team to be able to solve these very difficult problems. So while we need that mathematics, language is the real tool of engineering designers. So to recap, we have an iterative design process where we correct our errors as much as possible. We add knowledge to that to accelerate it, to make it happen in a time that is tractable. And then we have to work in a diverse team to maximize the amount of knowledge in terms of theoretical knowledge and in terms of experiential knowledge in what we're doing. So I hope you enjoyed that. And if you want to try and tackle some of the world's biggest problems, consider joining us at the James Watt School of Engineering at the University of Glasgow.